One of the things we're going to do in Module 5 is to teach you how to do shape analysis and to better understand scaling. So this is a part of organismal biology that has a long and venerable history. So scientists have been studying shapes since, well, at least as early as Galileo. And I've put an illustration here from a publication, one of his publications. And what he pointed out in this publication was you can take the same bone out of two different animals that have different body mass, and not they don't just change in size. One isn't just larger than the other, but the one bone isn't just larger, but they change in shape. And this has to do with the fact that the size of animals, as size increases, the strength of the material properties of the bone needs to either change, or the proportions of the bone need to change to account for relatively larger masses that their limbs are supporting. So we'll come back to that and I'll explain that again later, but I just wanted to point out that this has been thought about by some of the most brilliant people who've ever lived, and it's a fascinating area of biology. It's a really fascinating and important area of biology. So another noteworthy publication on this topic, excuse me, was by Darcy Thompson in 1917. He wrote a book called On Growth and Form, which is a pretty amazing book, but he talks about how you can mathematically study shape changes. And then in 1926, Haldane published a paper. It's a fairly short paper, but it was really instrumental in bringing this issue to the attention of biologists of the day. And this is a quote from Haldane. He said, "Comparative anatomy is largely the story of the struggle to increase surface in proportion to volume." So we're going to focus on looking at surface area to volume and length to surface area during this week. And it's fundamental to organismal design, and it's a rich topic for a capstone project. This slide illustrates a few examples of how different processes are related to different dimensions. So some processes scale with length, for example. Cost of transport is one of those. Limb length is directly correlated with cost of transport. Other processes, such as gas exchange in the lung or nutrient uptake in the gut, that depends, those processes, the rate of those processes depends on surface area. And the force of muscle is a function of cross-sectional area of the muscle. The strength of bone loaded under compression is a function of the cross-sectional area of the bone. And then things like basal metabolic rate or body mass, those are related to volume. So relative volume to cross-sectional area to length change as animals change in size. And the study of this is known as scaling. And this matters also not just to the individual organism, but it is important on an ecosystem or ecological level. So, the suitability of diets depends on body size, and extinction probabilities depend on body size, and growth rates and population growth rates and home range requirements, etc., etc. So body size is also important in a larger context. Organisms can change in size two different ways. They can scale geometrically similarly, and that's known as isometry, in which there are no changes in shape as they change in size. So if you took a photograph of a small and a large one, and you increase the size of the photograph of the small animal, it would look identical to the big animal. You put them side by side and they look the same. Whereas other animals undergo shape changes as they change size. And humans are a good example of this, and that's known as allometric scaling. I've illustrated that principle with these photographs. This is a normal looking baby. These people have normal proportions. put them side by side and really compare, I put these bars in so you'll see that really the top of the head and the bottom of the feet, where the chin is on the baby is about the armpits of an adult. The hip of this baby doesn't even reach midway up the thigh. So this just brings home the point that there are huge changes in shape as humans increase in size, as they change in size. So that's a size change with ontogeny. Here's another example. These are, you've got a colt and an adult horse, and you can see the colt's legs are nearly as long as the legs of the adult horse. So that's the opposite of what we saw with the baby, right? The baby had these really short legs and the adult really long legs. In a horse, that baby, the juvenile, has these really long legs relative to its body size, relative to its total body mass. So this is also a sort of ontogenetic allometric scaling, but it's for those limb proportions, it's changing in exactly the opposite way as with humans. You see this again in giraffes. So the baby giraffe has limbs that are, in fact, proportionately longer than the adult, right? They're just enormously long limbs for the relative size of the animal. And again, that's opposite to what we saw with humans. This is an example of isometric scaling. So this is an adult and juveniles of amphibians, and it's pretty common in amphibians to have isometric scaling. And what I did here was to make the point is I actually photoshopped this slide. I actually tried to illustrate the point that if you simply take the photograph and modify the size, then it's hard to distinguish the individuals. So the third little one, the third juvenile, it's sitting on the log, is actually been added in, and that's the adult. And I just simply clipped the photo and then shrunk it and made it the same size as the juveniles. And you really can't pick that out very easily. So that's isometric scaling. The easiest way to understand the math behind scaling is to look at a very simple geometric structure. So yes, animals do scale isometrically or geometrically similarly, but we'll come back to thinking about the relationship of surface area to volume in frogs and in other animals. But right now I just want to turn your attention to a simple geometric shape, a cube.
Consider a cube with a length of 1 centimeter, a height of 1 centimeter, and a depth of 1 centimeter. The surface area of this cube is simply the width multiplied by the height, and that will give you the surface area for one face. And since there are 6 faces, then you multiply that again by 6. So the length is 1 centimeter, but the surface area is 6 centimeters squared. The volume is the width by the height by the depth, and that is 1 cubic centimeter. So the length is a function of the length to the first power. The surface area is a function of the length raised to the second power, and the volume is a function of the length to the third power. If we double the length, and that's shown on cube 2, now the surface area is this width multiplied by the height multiplied by 6 for the 6 faces, 24 centimeters squared. So the length doubled, but the surface area went up by a factor of 4. And the volume would be 2 centimeters multiplied by 2 centimeters multiplied by the depth, 2 centimeters. So that's 8 cubic centimeters. So the volume increased by 8, surface area increased by 4, length increased by 2. If you look at the ratio of the change in the surface area to volume in cube A, in this smaller cube, the ratio was 6 centimeters squared to 1 cubic centimeter. In cube 2, the ratio is 24 centimeters squared to 8 cubic centimeters. So that's 3. Instead of 6 to 1, you have 3 to 1. So that ratio is decreased. The smaller cube has relatively more surface area for its volume. And the trend is going to be the same if you look at cube 3. That has double the length of cube 2, so it has a width of 4 centimeters, a height of 4 centimeters, a depth of 4 centimeters. And you compute that ratio, 96 to 64, that's even smaller. So the surface area to volume ratio is even smaller. So the bigger an animal gets, or the bigger, if something is scaling isometrically, as it increases in size, the surface area does not increase in proportion to the volume. And so if an animal is relying on surface area of the skin, for example, to gas exchange, like amphibians do, this becomes an issue. So it's harder and harder and harder for big animals to rely on their skin for surface area because it's not increasing relative to the rate of increase of the metabolic rate. So this is really important to understand these relative proportional changes as shapes increase in size. It turns out to be quite useful to express these relationships in terms of logs. So transforming the data to a log scale. And one of the reasons for that is because the relationship between the length of a cube and the surface area is an exponential function, or the length to the volume, or the surface area to the volume. So they're not linearly related, as we just discussed. And so if you work with your arithmetic coordinates, here's an example of a bunch of different cubes. These are the volumes plotted on the x-axis, and this is the surface area. And you can see that it's not a linear function. If this exponent were 1, you'd have a line here. But we already know that the surface area is getting relatively smaller for the volume of the cube when you work with this on arithmetic coordinates. However, if you take the log of this relationship, it straightens this out. So you either take the log and plot this on an arithmetic scale, or you could just plot it on a log-log scale and not do a transformation. So surface area is proportional to some constant multiplied by the volume to the 2/3. So surface area is a function of the constant times the volume, which is a function of basically length cubed, but the surface area is the volume to the 2/3. If you take the log of that, this exponent comes down. You get rid of it, right? You no longer have a 2/3 exponent. So you take the log, both of these sides. Take the log of the surface area, the log of this, and this is the equation you get, and plot that. Now you've got a line. This offset is the y-intercept, is dependent on the shape. So, it's 6 for a cube. It would be a different number for a sphere. It would be a different number for an amphibian. However, the slope of the line wouldn't be. So the offset here changes, but the slope of the line doesn't change. For every isometrically scaling shape, as it increases in size, if you take the log of the surface area and plot it with the log of the volume, the slope will always be 2/3, always be 0.67. So that's pretty useful. This slide illustrates another reason that biologists use log scales to express their data, and that is related to the enormous range of the data that they study. So, for example, if you wanted to understand the surface area of an animal, and just look among chordates, the surface area of that animal relative to its mass, and look at all chordates, it's a whopping big scale. Amphioxus, which isn't the smallest chordate, tunicates are smaller, larval tunicates are at least an order of magnitude smaller than this. But Amphioxus, it has a mass of about 0.000 kilograms, right? It's this little tiny animal, and its relative is the great blue whale, and it has a body mass. The great blue whale has a body mass of 170,000 kilograms. So this is a ridiculous 9 orders of magnitude. That's a huge range in scale. And to put your data onto an arithmetic graph means that most of your animals are squashed into a range of the scale where you can't even read it. So here's an example. The whale isn't on here. This is the famous mouse to elephant curve. So what is plotted here on log, natural log, or not natural log, log base 10 scale across the x-axis is body mass. And then on the y-axis is metabolic rate. And that's been measured. These are all mammals. For a mouse, they run around 30 grams, right? And little birds versus an elephant. So an elephant is, I mean, if you want to put that blue whale on here, 170,000 kilograms, you'd be up here, right? You'd see it, though. It would be up here somewhere. If you put this on arithmetic, if you put all these data on arithmetic graph, all of these animals, because a whale is so much bigger, they would just be all scrunched into the left-hand corner of your graph. You wouldn't be able to say, oh, this is interesting. The residual for the boar, it's above the regression. This is much higher metabolic rate. Why do boars have high metabolic rates? Oh, what's going on with this marmot? Why is it so low? It would all just be squished into one little point. So the log scale, when you're working with these huge ranges, like many organismal biologists work with, becomes important in just seeing your data and being able to understand it and interpret it. So that's one major advantage of either plotting the data on a log scale or transforming the data to logs and plotting on an arithmetic scale. I'm sorry, I realize I misspoke, and I said these were all mammals plotted on this graph. That's not correct, obviously. These are endotherms. These are animals that generate heat internally to maintain body temperature. So you have small birds, you have a hen, you have a cock, blah, blah, blah. This slope is quite different for ectotherms. So if you were to just plot snakes on here, or if you were just to plot crocs on here, or some grasshoppers, whatever, you wouldn't get a slope of 0.75. So I said all mammals. What I meant was all endotherms. So the slope for ectotherms in terms of the scaling of their body mass to metabolic rate is much closer to 1. So anyway, excuse me. So the second major reason to use logs and to plot your data on a log scale, or to convert your data to transform it to logs, is because then you have this whole tool chest of statistical techniques to understand your data. You can put a line to it. You can do all sorts of, you can create linear models basically and use these statistical techniques to ask questions about differences or similarities, etc. So part of this use, the reason that biologists use logs and to transform their data is to be able to have access to these powerful statistical tools. that covers the basics of scaling and the way that biologists like to work with numbers and use logs and deal with scaling. However, I'd like to introduce a couple of terms. So first is the idea that when animals do not scale isometrically, they will scale with either positive or negative velometry. So that's illustrated on this slide. So if the slope, let's say you're looking at amphibians, and the surface area to volume ratio is exactly as you would predict for a cube, never mind the offset, right? But the slope of the line, once you plot these data on a log scale, the slope of the line is 0.67. You'd say that's isometric scaling. They're scaling just like frogs scale. But if the slope is higher, that's positive velometry. So basically, think about this. For a given body mass, you have more surface area than you would expect. And then you might have lineages that scale with negative velometry. For a given body mass, they are not increasing like a cube or a sphere or a frog. They have less surface area than you would expect if you were just scaling that cube. So positive and negative velometry then give you some insight into how these animals' proportions are changing when body mass changes. I'd like to sum up with this slide, and what I'd like you to do to test your comprehension is to pick out which line describes the ontogenetic scaling relationship for humans, which line describes the relationship for horses, and which line describes the relationship of amphibians, for amphibians. So you should be able to just look at what you would expect if you plot the leg length series of amphibians versus the volume or the mass of the animal. You could predict, since they scale isometrically, which of these slopes belongs to the amphibian, which of these lines, which belongs to the horse. You know that they have relatively long legs as juveniles for their body mass, and the body mass grows faster than the legs are going to grow, and the opposite is going to be the case for humans. So if you can pick out these lines, I'm not going to tell you what they are, but if you can just reason that through and pick out those lines, then you've got this, you understand this. If that seems tricky to you, then maybe rewatch this lecture or come to office hours, talk to me, set up an appointment. This is quite an important concept, and it's a little bit trickier than it seems at first. So just past experience say sometimes people struggle a little bit when they're first presented with this concept of positive and negative velometry and trying to sort out how organisms are scaling as they change in size. So don't hesitate to get a hold of me or Mark. We're here to help.